lesson 10.5. This is called tangents. And I'm going to go over the warm-up problems quick. Go to review for our quiz tomorrow. Okay. Last lesson we talked about inscribed angles. So an inscribed angle is an angle whose vertex lies somewhere in the circle, and the endpoints of the angle, the two segments that form the angle, are somewhere on the circle, and we call this piece that it intersects the intercepted arc. Okay, who remembers the relationship between the intercepted arc and the inscribed angle? Alejandro?
The inscribed angle is half of the intercepted arc.
Perfect. He said the inscribed angle is exactly half of the intercepted arc. Good job. So half of 46 is 23 degrees since we're measuring an angle. Good. Just half of that. So this one is kind of going the other way. We know what the inscribed angle is. And so I know that angle is half of this measure, but this time I don't know that measure. I know the angle, so I would just have to double it. This should really have an arc symbol over it, if you want to draw it in. So that's 156 degrees is what that arc measure should be. Okay, remember that? Good. That was one of the things we learned. Another thing we learned was if two different inscribed angles intersect the same arc. So looking here, like this inscribed angle is intercepting arc AD, and so is this inscribed angle is intercepting that arc as well. Then those have to be congruent because they're both going to be half of whatever the measure of that arc is. So they have to be the same. So you should have just set those angles equal to each other. And here the directions just told us to find the value of x. I solved that and I got x to be 19 using algebra. All right, so then this one is similar. I have this inscribed angle, which is intercepting that arc, and this inscribed angle that's intercepting this arc. So I know those measures both have to be half of that arc measure, so they have to be the same thing. Okay, those 4 problems should have taken you about like 1 minute. Now here they didn't just ask for x though. They asked us to actually find the measure of arc MN. All right, so a couple ways you could do this. I found the measure of this angle after I found x. I just called it angle O because I knew it was x, which is 20 plus 23 degrees. So I knew that inscribed angle was 43 degrees. Okay, so based on what we just talked about, it's always half of that intercepted arc. So to find that arc, I would just double that. 86 degrees. To get that final answer. Okay, any questions on those so far? Pretty straightforward. Another theorem, we learned like 4 different theorems in this lesson. Another theorem we talked about was if the inscribed angle intercepted an arc that was a semicircle, it's still half of that measure. Half of 180 is 90, then it's a right angle. So another thing we talked about was if you connect those two, obviously in the semicircle, that third like side to this triangle right here would be a diameter length. Okay. So basically we said like this would always form a right triangle. Okay, meaning I have a 90-degree angle, this angle, and this angle. So 2 ways you could do this. You could add them all together and total them how many degrees in a triangle? 180, good. Or what do these two have to total? 90. That's what I did, just to make it a little bit easier. I was like, all right, well, these two together have to total 90 if the other angle's a right angle. So I got x to be 14 for that one. Okay. This one, same thing. I have this inscribed angle that intercepts the semicircle, so that's going to be a right angle, and it forms a right triangle with the diameter. This time, x is on one of my side lengths. How can I find x here? Pythag would work, agreed. This is a right triangle. We can use Pythag. Nice, Tyson. X squared plus 14 squared equals 17 squared. I think that's what I got. X is the square root of 93 as a decimal. 9.6. Okay. Last one. Another thing we learned. Wow, what a great lesson. We learned so many new things. Another theorem was if you have an inscribed polygon, inscribed meaning its vertices lie in the circle. Do you guys remember what's true about the opposite angles? Nope. They're supplementary. They total 180. Good guess. So here to find x, 3x plus 1 plus its opposite angle are supplementary. They have to total 180. You'd set up your equation like this. I got x to be 33. So there's a set of opposite angles. The y's, the angles with the y variables, are a set of opposite angles. So those have to total 180 as well. And I got y to be 18. All right. That was a lot of warming up. But great review for a Monday. Any questions? All right. We are learning a very, 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 very important vocab word today. We use it all the time in calculus. So if you ever get there in your math career, today's the day where you learn it for the first time. It's called tangent or tangency, and it's different from the SOHCAHTOA tangent. They're the same word, they're spelled the same. Tangent, when I'm talking about SOHCAHTOA, represents a ratio in a right triangle. This tangent means something different. This tangent means, and usually it's in a form of a line, it can be a ray or a line segment, but it means it intersects at exactly one point. So if I have a line that's tangent to a circle, it means it intersects the circle at exactly one point. Okay? So this would not be tangent, because how many times does that intersect in my circle? Twice. That's called something different. That's called secant. That you don't have to know yet. But if I have something like so, and picture taking a line and just kind of like kissing the top of the circle here, where it just intersects at one point, we call that point the point of tangency. And we call the line the actual tangent line. Or we say that line is tangent to the circle. So intersects at exactly one point is what tangent means. If you ever do take calculus, the whole I'd say 30% of calculus is we take different curves and I give them a point on the curve and I said, okay, find the equation of the tangent line at that curve. So they figure out where it intersects exactly at that one point, and then they come up with the equation of that line. We use some algebra skills. We use point slope form. We talk about slope all the time. And then obviously our vocab of knowing what tangent means. All right, so common tangent is a line, ray, or a segment that is tangent to two circles in the same plane. So it's basically if I have two different circles and I can draw one line that intersects my circle exactly once, then that'd be a common tangent line. Okay? They could also share the point of tangency. So I have line L here, and it's tangent to F at exactly one point, tangent to G at exactly one point. I could draw in a couple more common tangent lines here. If you have a straight edge, this is nice, but it's kind of hard if you don't have a straight edge. You guys agreed? I could draw one kind of up there where it intersects twice. Well, I should say once on each circle. Okay. Common tangent. I could draw one down here. Common tangent. All right, so that's what a common tangent is. That's kind of our big vocab for today. All right, here it says, draw in the common tangents. If none exist, write no common tangents. These are kind of fun. You basically take your straight edge, and you're trying to figure out how many lines you could draw that intersect each circle exactly once. So just kind of like the last example, I could kind of do something like this that lies above it. And it's intersecting here once, here once. Make sure you draw arrows on your tangent lines. Okay, I could kind of do something below it like so. That intersects exactly once. Anybody else come up with another one? Can I do something like this? No. Oh, phone's ringing. All right, you guys try the next one or two. Oh, this is good. No, she's not. She told me, oh my gosh, she's my RTI. She told me she wasn't going to be here and keep up the line. I don't think so. She said she had to go somewhere. Yeah. Yeah, she did tell me. Yep. Bye. Okay, this one had 2 tangents. What do you think about this one? None. There's no way I could draw a tangent line to the inner circle without intersecting. Well, I guess if I drew a ray, that would be tangent here. All right, none. You want to think of tangency as like it just like kisses it. All right, here, a couple different options here. So, kind of went like above again. And below. Where else? Tyson?
Crossing through the middle of the circles.
Okay, what were you going to say?
No, same thing.
Same thing. We could do one kind of like this. Let's see if I can move that a little bit. Oh, shoot. Is that my phone again? I think that's my 7's. I can't change my steepness. Okay. You get my gist. Picture that's just kissing it. And we can do that both ways. It's easier if you have a straight edge. I found 4 tangents there. All right. So basically, let's talk about 2 theorems today. Okay, they involve tangent lines, now that we know what tangent lines are. Here's our first theorem. A line is tangent to a circle if and only if it's perpendicular to the radius, or a diameter for that matter, drawn to the point of tangency. Okay, so I do kind of a little visual for this one. So I have 2 tangent lines here. I can kind of slide these around if I want to. I have my purple tangent line and my green. So what this theorem is saying is no matter where your point of tangency is, if you draw a radius or you draw a diameter, it's always going to be perpendicular. And you can kind of picture this, perpendicular at that point of tangency, perpendicular to the tangent line. Okay? So let me just slide them over here for a second, something like this. If you draw a radius, it's always going to be perpendicular to the point of tangency. There's a problem like this that we did in Algebra 2, and they all forgot that from geometry. I was like, oh, we're learning that today. How at the point of tangency, it forms a right angle. So line L can only be a tangent line. This can only be a tangent line if and only if it's perpendicular to a radius of the circle or diameter. If and only if L is perpendicular to ST. Okay, so let's try a couple of these. This example says JL is a radius of circle J. So they're telling me this length of 8 is a radius. Determine whether line KL is tangent, you can extend it if you want, is that line tangent to circle J? Well, based on what we talked about, if and only if at this point L, it's perpendicular to that radius. Okay? Now they're helping you out a little bit. They're showing you this segment to here from point K to this point on my circle is 9. What would this length be? 8. How'd you know that?
Radius.
It's a radius length. Agreed? 8. And then we can see we have this right triangle formed here. And this whole hypotenuse, if this is indeed is a tangent, is 17. So what we're going to do to determine if this is a right triangle is we're going to use Pythag. And then we can conclude, yep, that is perpendicular to that because it forms a right angle, forms a right triangle. All right. You guys kind of did this in chapter 8 where I gave you 3 side lengths and I said, first determine if this can even form a triangle, then determine if it's a right, acute, or obtuse, and use Pythag to do that. So we're not really proving it's a triangle, we're just proving this is a right angle. Okay? But it forms a triangle. So we can do the 2 legs squared. So 8 squared plus 15 squared. Does that equal 17 squared? Evaluate this number. I got 289. 17 squared is 289. Since Pythag holds, yes. That means this has to be a right triangle, meaning that radius JL is perpendicular to the point of or perpendicular at the point of tangency at point L, perpendicular to the tangent line, however you want to say it. I would just say KL is indeed tangent to circle J because angle JLK is a right angle. So JL is perpendicular to KL. That'd be an easy way to justify your answer like they asked us to. All right, one more. Like this. In this figure, they're telling me WE is indeed tangent to circle D. So what that means, it's tangent to circle D, means it's perpendicular to any radius or diameter I draw. So they're telling me this is a right angle. I know it's tangent to that circle. It's going to form a right angle with the radius or diameter. Find the value of x. Okay, so x is my radius length. And again, you can see that they're showing you that distance is 16 to that point E. So again, we're going to set up Pythag, where I have x squared plus 24 squared equals Yeah, team, what's that whole hypotenuse?
Plus x squared.
Good. I'm going to call it x plus 16. Put that in parentheses. Squared. All right. 24 squared is 576. I'm going to give you 1 minute to tell me what this is. If you tell me that's x squared plus 256, I'm going to call you out. Matthew. Oh, wait, no, you didn't do that. Okay. I did. Lauren! Lauren. Call that trash algebra. This, x plus 16 times itself twice.
Oh.
Don't worry, you're literally, people make that mistake all the time. That's why I make a big deal out of it. All right, x squared. How many of us remember to do this? Be honest. Did you say x squared plus 256?
No.
Okay, good. Did you, Malin? Malin.
I didn't.
Oh, okay. Did you?
No. That's
Jeez, why am I?
Big fan.
Yeah, I get that.
They hung up already.
All through.
All right. So.
Thank you.
Oh my gosh.
Making you right now.
I know. I have problems with my smartboard. Okay, this is what we should get. I'm just gonna come on here. What I said that was 5 to 76. 32x plus 256. All right, what happens when I go to combine my x squares? They drop out. X squared minus x squared is 0. No more x squareds. So I'm left with this. Let's see, that's 320. X is 10. Is that all we had to find was x? Yep. Okay. One last theorem we gotta talk about. Next theorem says if two segments from the same exterior point, what do we think the word exterior point would mean?
Outside.
Outside the circle, are tangent to the circle, then they are congruent. All right, so let's take a look at this on decimals. So what this is saying is, all right, here we go. Exterior point somewhere outside the circle, and it has a line that's tangent to the circle, like the purple line, and another line that goes through that point that's tangent to the circle. They're telling you this distance is going to be the same. Which, again, we can kind of visualize that here.
Could you report to Mr. Bufflo's room?
Okay, if I moved it even closer, we can still visualize that those look like they'd be about the same length. And that's what this theorem allows you to include. As long as they share a common point and they're both tangent to the circle, then those lengths are going to be congruent. So in this picture right here, as long as AB and BC are both tangent and they share this common point, then those segments are going to be congruent. AB is congruent to BC or CB. Okay, so pretty easy example here. They're telling me AC and BC are both tangent to Z and they share this common exterior point. So this theorem says these have to be congruent or the same length. How would I set up an equation? Set them equal to each other. These are the same length, so this distance must be the same as this distance. X is 5. All right, last problem. This one first says find the value of x, and then we're going to find the perimeter they're talking about of the outside, not the inscribed circle. Okay, I want you guys to try this. I'm just going to give you like 30 seconds. See if you can figure out what x would be. X is right here. Okay, any guesses? Alejandro? 8. Other guesses?
I had 8.
8. 6. Other guesses? You got 6 too.
Yeah.
Okay. You got 8. Anybody else? Anybody want to go 7 in between?
I'll go for 7. No.
Tech?
What'd you get?
Siler, are you sleeping? Don't worry. I see Siler's dad every day. So if Siler's ever slacking, I just gotta let him know.
Tyler would never slacking.
I just gotta let Donnie know.
Oh, please don't.
Well, don't sleep in my presence.
He's always focusing his.
No, it's on Monday.
You say that about every day.
Exactly.
Because it's Monday.
All right, Siler, what do you think X is here?
Yes.
Alright. It's gotta be. Oh, let me make. No, actually,
You sound like Beetlejuice.
These poor people who are gone today trying to just finish the notes and watch this YouTube video. We're just waiting on Siler.
It's a carrot.
Carrot.
You got 10 seconds. 10, 9, 8.
No.
Guess it. Figure it out.
I was trying to figure out, and you rushed me, so I'm not doing it.
All right, do you just have a guess?
No, I was still working out the problem.
Okay.
You have no
Stop
idea.
selling on the wrong page.
All right. Okay, we're done waiting for you. All right. So the right answer is 8. 8 is right. 8 is right. Okay, here's why. Look at point A. So there's 4 points of tangency. Do you guys see that? So here's a tangent line. Here's a tangent line. And if they share point A, these distances are congruent. So if this is 5, this is also 5. With me? This whole segment is 13. So what's this length? 8. 13 minus 5 is 8. All right, another tangent line that shares the exterior point B is this one. The one with X. Equidistance, X also has to be 8.
You laugh out, Malin.
Ew.
All right, now we need to find the perimeter. Calm down. So I'm going to start here actually at point L. So to find this perimeter, I have 5 and 5. I have 2 5s. 2 lengths of 5. And then I can go 8 and 8. With me? This would be 7 and how long? 7. And then 6 and 6. Good. $52 centimeters. Okay, we're finished. That was rough.
What are you talking about?
Sorry.